let's talk about the idea of continuity and one-sided limits. Now, like usual, let's quickly take a look at the learning objectives so you get an idea of what it is you should be getting out of these next several videos. First thing is we want to determine continuity at a point and on an open interval. We need to define what those two things mean and work out a few examples so you understand the concept there. We want to determine one-sided limits and continuity on a closed interval. To determine continuity on a closed interval, we really need this idea of one-sided limits. Take a look at some properties of continuity, and we're going to investigate what's known as the intermediate value theorem. Now, let's just jump in here real quick with a quick definition. A function f is said to be continuous at x equals c, so c is some value, so c is an element of the real, so it's a real number, if the limit as x approaches c of f of x is equal to f of c, where obviously f of c, on limits quite often we say L, but L has to be f of c, and this is obviously also a real number. If it was not a real number, then the limit wouldn't exist to begin with. What this means is that the limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x, which is equal to f of c, which is in fact a real number. So I can come down here and let's just draw a couple of quick graphs to see what we're talking about here. So say here's the value of c, and let's just say my function looks something like this. Now, as x approaches c from the right and x approaches c from the left, my function is coming like this. This point right here is f of c, and the limit from the left is equal to the limit from the right, which is this value f of c. So this function is continuous at this point c. If I draw to the best I can the same function, and let's just say there was a hole right there. See, now as x approaches from the right and the left, it approaches a hole. Now the limit may be L. These two actually have the same limit, but L in this case is not equal to f of c, because in this case f of c does not exist. In this case, L is equal to, whoops, that should be f of c, not f of x. So this function is discontinuous at this point. I haven't said anything about the rest of these points, just some specific point c. This point is continuous at this specific point c. Now, a function is continuous on an open interval on a to b. So I'm going to take c, and I'm going to come around to a to b. Same thing here. Some open interval, a to b. If is continuous at each point in the interval. That's every point on the interval. In this case, over here, this is continuous on the open interval, a to b. This one is not, because it's not continuous at c. Now, a function that's continuous everywhere from negative infinity to infinity is said to be, and I kind of ran out of room there, I'll slip it in right down here, continuous everywhere. All polynomials are continuous everywhere. That's a quick example. All polynomials. That's supposed to be an S.